So welcome back to my lectures on Galois theory. Today we are going to start a new topic called geometric constructions. Constructions. And in this topic, what we are going to do is we are going to build a sequence of extensions over the real number, so the rational numbers q. It's an infinite sequence of extensions over the field of rational numbers. And the property of this extension is, if you take any two adjacent extensions like j plus 1 over j, let us take it as q0, is always 2. The degree of an extension over the adjacent extension is always 2. The elements of these extensions are called constructible numbers. So we are going to construct now some numbers, and those are the elements of this sequence. And these numbers are constructed using a set of rules. They are all, it's a geometrically constructed numbers, and it follows a specific rule. So let us start with those rules. Rules. The first rule is 2 points are given. Two points are given. Meaning there is a point here P, there is a point here Q. Then second rule is the distance between these 2 points is 1 unit. And third one is 0 is the distance between the same points. Same point. That means the distance between P and P, or Q and Q. So these are the first two elements that is going to come into our field. So these are the two. So the first two constructible points or numbers are 0 and 1. 0 is obtained by finding the distance between the point and itself. And 1 is the distance between the given 2 points. The fourth rule is a straight edge can be drawn joining 2 points, 2 known points. 2 known points. Known points mean we are going to find some more points using this rule, and you can take any of those points and draw a line. Known points. And the fifth rule is a compass is given. Compass means, you can point in one point. You can fix in one point and draw a circle with the other leg of the compass. A compass is given to draw a circle with a known point as center and a known number, known constructible number as radius. So these are the rules, and we are going to find out what types of constructible numbers we can build from these rules. Now let us assume that we know 2 points, P and Q, and there is another point somewhere on the line or outside, let's say R. And suppose you want to draw a perpendicular line on this. These 3 are points which we know. We only know right now P and Q, but let us assume that we know another point that we are going to find. Okay. Before that, I need some more tools here. So let us take another point R outside or on the line, and we want to draw a perpendicular line. That is possible because use the compass and mark 2 points here, equal points, more than the distance between this, any point more than the perpendicular distance from here. That is possible. And take these 2 points and mark the same radius, mark 2 points here. So you can draw a line like this. This will be perpendicular. So given a line and a point, you can draw a perpendicular line. Line is possible. Similarly, there is a point here outside PQ, and you want to draw a line parallel to that. So what do? First you draw the perpendicular line and draw another perpendicular line. So you can draw a parallel line also. So parallel lines can be drawn using the rules that we assumed. So we have only two constructible numbers, 0 and 1. That is from the rules. So this is our 0 and this is 1. I'm going to give it a P. This OP and this distance is 1. And 0 is the distance from O to O. So these are constructible numbers from the rules. Using the compass, you can construct the same distance here, same distance here, same distance here. So you can construct 2, 3, 4, etc. and -1, -2, etc. So if 0 and 1s are constructible, then so are 0, 1, 2, 3, etc. -1, -2, etc. So these are, if these are constructible, then these are also constructible. Now let us assume that alpha and beta are constructible. And I'm assuming beta is different from 0. Then let us mark OP as alpha, and from here you mark beta here, Q, that is beta, then OQ will be alpha plus beta. And if you mark it on the left side, let's say S, then OQ is equal to alpha plus beta, OS is equal to alpha minus beta. So if alpha and beta are constructible, so are alpha plus beta and alpha minus beta. Now, alpha is constructible, so OP alpha. Draw an angle, any angle. You can draw any angle. Take an arbitrary point and draw a line like this. And mark 1 here. Possible, because 1 is given. And mark also the beta. So this is our Q, this is our R. Then you join R and P. Then draw a parallel line through Q to RP. Let us make it as S. Because these two lines are parallel, these two triangles are similar. That means triangle OPR is similar to triangle OSQ. That means OP by OS equal to OR by OQ. And that means OP is what? Alpha. OS we don't know. OR 1 by beta implies OS equal to alpha beta. So this is actually alpha beta. So if alpha and beta are known, this is our beta. If alpha and beta are known, then this is alpha beta. So alpha beta can write alpha minus beta and alpha beta. Both are known. All the three expressions are known. Now let us assume, let us draw another figure. OP again This is our alpha, and draw any angle and mark 1 here. This is our R, this is 1, and mark also beta here, and that is our Q. This is beta. Then you join Q and P and draw the parallel line through R to PQ and make it as S. So these two triangles are similar again. So OS by OP is equal to OR by OQ. OS we don't know. OP is alpha. OR is 1. OQ is beta. That implies OS equal to alpha by beta. So alpha by are also constructible. If alpha and beta are constructible, these are constructible. So this, what we have is only the integers. So we can construct 1 by 2, 2 by 3, 4 by 6, all we can construct because alpha by beta is constructible. So this implies any element of the form P by Q, P and Q belongs to Z are constructible. That implies Q is constructible. So now we already constructed every point in the field of rational numbers with the rules and the given 2 points. Can we find another number outside Q? Can we find constructible numbers outside Q? Well, we are going to do this in an analytical way, not in the geometrical way. So let us say you have 4 points, PQ and probably RS. Okay, then we can join this. You can join this and you can also join this. So you are getting a totally different point here. You are constructing a point here other than these 4 points. Okay, and also we can, this is case 1. Case 2, you can draw a circle and go another circle. Then you can get 2 points here. You know only these 2, P and Q, and this R, R1, R2. But still you can get 2 different points. That is probably R and S. And case 3, you can get, we draw a circle, this is P and R1, and you can draw you can draw a line, let's say you know these two numbers, R and S, and you join and it cuts in maximum 2 points. So this is probably Q and O. So given the points, you can construct more points here. But question is, are these points inside Q or outside Q? If it's inside Q, we are not interested because we already have Q. If it's outside Q, yes, we are interested. So these are two linear equations. So this will be ax plus by equal to c, or a1 plus b1 equal to c1. This will be equal to a2x plus b2y equal to c2. How do you find this number? This is, you solve. If you solve, a1, b1 and c1 are from Q. a2, b2 and c2 are from Q. And definitely x and y are from Q. So this point is not different from Q. So this point, let's say this point, that I'm going to say it as T belongs to Q. So we are not interested in this situation. This situation can be reduced to this situation because these 2 points are same as this circle intersected by this line. So you can reduce, see here also we are going to solve these 2 equations. But if you solve this equation, you can reduce 2 equations with a equation of a circle and an equation of a line. And that is nothing but here. So these 2 are similar. We don't need to consider this in different cases. So case 1 and case 2 are similar. Here, the general equation of a circle is x square plus y square plus ax plus by plus c equal to 0. And this one you can take it as px plus qy plus r is equal to 0. When you solve this equation, you get these 2 points. And these 2 points actually will be the, what will happen here. So when we solve this equation, we might get or we can get, depending on the values of radius and this line, we can get numbers of the form root of alpha. Because finally we are going to solve a quadratic equation, and when you do the quadratic equation, the result is going to be like minus b plus or minus root of b square minus 4ac by 2a. So once you solve this one, you can get something like root of a or root of alpha. This will be always positive because the nature of the circle and this is not any quadratic equation. It's a quadratic equation of a circle and a line. See, so the coefficient of x square and the coefficient of y square are same. And we don't have xy and all stuff. So here we are not adding any new numbers. This is equivalent to this, but this can generate constructible numbers of the form root of alpha, where alpha belongs to Q. At this point, we know only alpha rational numbers. So these are all rational numbers. So we know only rational numbers at this point. We are going to find more, but until now, this will be of the form root of alpha, where Q belongs to Q. Alpha belongs to Q. Now we are going to construct the first extension of the field of rational numbers. So we already know that we can build all the rational numbers. This we all know. And we know that if alpha, beta are given, then alpha plus beta, alpha beta, alpha minus beta, alpha beta, and alpha or beta are known or can be constructed. Can be constructed. Then we know that for alpha belongs to Q, root alpha can be constructed. How? By drawing the proper circle and a line. So what does this mean? So we know root alpha and we know any numbers from Q. So you can say beta plus root alpha can be constructed, or gamma plus beta root alpha can be constructed. So all these kind of numbers can be constructed. Where are these coming from? These are actually the symbol coming from the symbol extension of alpha over Q. So if you know root alpha can be constructed, then Q of root alpha can be constructed. So that is what? That is actually Q is a subfield of Q of root alpha, or Q alpha is an extension of this with the degree So one thing which we missed earlier is that if you know 2 points P and Q, there is a way of finding out the midpoint using compass. So what you do is you mark 2 arcs, more than the half of it, like this, one from here and one from here and one from here and one from here. Then you join these two, this will be the midpoint. So we can always find the midpoint of P and Q. Or other words, you know the distance here, and this is half of by 2 is also constructible. So we know this portion. Okay, with this, suppose alpha is known or alpha is constructible. Alpha is constructible. Then what you do is you draw a line and you start from one point, you take one unit. This is our Q, this is our P, or this is our O. Let's take O. And from O, mark the point alpha. This is 1. This is any constructible point, doesn't need to be in Q. It could be within Q of root alpha. Now get the midpoint of this and draw a semicircle. So this is equal to this. Then draw a perpendicular line here. You can all do this. Not from here, sorry. Not from here. Sorry. This is a center of the semicircle, and you draw a line, perpendicular line here. Let us call this one as R. So if you join these two triangles are similar. Actually, this is equal to this, and this angle is equal to this angle. So what do you do? These two are similar triangles. So OQ by OP is equal to not OQ, I'm sorry. OQ is opposite of this angle, so opposite of this angle will be OR is equal to OQ OR by OP. What is OQ? OQ is equal to 1. What is OR? We don't know. What is OP? Alpha. This means OR square equal to alpha, OR is equal to root alpha. So that means if you know alpha, you can construct root alpha. So root alpha is constructible whenever alpha is constructible. What does that mean? You can construct 2, so you can construct root 2, so you can construct root of root 2, so you can construct root of root 2, goes like this. That's what it means. So let us see what are the elements in the field of constructible numbers. So field of constructible numbers. Field of all constructible numbers. exactly it contains those elements obtained from Q and finite number of square roots of elements from Q by finite field operations. What I mean is, this contains, let's call it as Q bar or Q prime. This is the field of all constructible numbers. I'm going to write the examples of this. You can have all Q's, 2, 3, 2 by 3, 1 by 4, etc. Then all roots, root 2, root 3, root of 2 by 3, etc. And roots of this, root of root 2, root of root 3, root of 2 by 3, etc. Another, you can do this finite number of times. Let's say root of 15 times, then another root of 2 of this form. And the numbers obtained by finite field operations of these collections, like it will be 3 root 2, 1 plus 3 root 2 minus 4 times root of root 2 plus 6 root 3 times root of 7. Finite number of field operations, meaning you are multiplying two numbers, adding, subtracting, all this kind of stuff. So this belongs to our Q prime. Now let us see an alpha belongs to, let alpha be a constructible number and alpha does not belong to Q. Then let us assume, for example, root 2 plus root 3. See, this belongs to Q of root 2 comma root 3. And that actually, right? So we can write this as Q of root 2, Q of root 2 of root 3. Okay, so this actually does not belong to Q. See, any constructible number will be of this form, not necessarily like this, but it has to be finite number of field operations of square roots of elements from Q, if it is not belong to Q. So if it is actually 1 plus root 3, then actually this belongs to Q of root 3. So you can write it like this: Q q of root 3. Let us take another one, q of root of 3 plus root 3. So this is actually belongs to q of root 3 root 2 of root 3. This can be written as q of root 2 root 3. So this is going to be q is contained in q of root 2, which is contained in q of root 2 of root 2, which is contained in q of root 2 root of root 2 root 3. In every case, if you take the degree of adjacent extensions, for example, in here the degree of q of root 2 over q is equal to 2, and degree of q of root 2 root 3 over root 2 is 2. Similarly here and similarly here. So that is what we are going to write. Then there exists alpha 1, alpha 2 dash dash alpha r constructible numbers are such that alpha belongs to q of alpha 1 dash dash alpha n, sorry, alpha r, such that q of alpha 1 dash dash alpha j colon q of alpha 1 dash dash alpha j minus 1, the degree of this equal to 2, or the degree of q of alpha 1 dash dash alpha r comma q is equal to 2 to the power of r. This is what we will be talking about. We are building a sequence of extensions of q with a property that the degree of adjacent extensions is